We are back again with chiller capacity control in Siemens PCS 7 tutorial. First, I will explain the process, and then I will show you how to develop this program in SCL. The whole control and simulation is done in SCL. We have just simple CFC components to do the indication and some basic faceplates to create basic faceplates. So we should go to the PCS7 environment. You can see it's a somehow simplified version of a chiller in an industrial setting. We have the air input from here and the cooled version of a pressurized air will be transferred here. The temperature for input air considered to be 50. Normal condition, consider the compressed air is around 30, 35, 40, but we consider the harsh or the extreme air temperature here. We use this chiller with a chilling system. In the chilling system, we have two compressors with some capacity control valves on the compressor. When the compressor is running, the temperature should be decreased, and when we need more capacity, this 75% valve will be in service. Then if we need more capacity, this 100% valve should be enabled. If we need more capacity, compressor 2, more capacity, the next valve, and if we need more capacity, the next valve. It's a discrete. These are discrete objects. A compressor is on-off object. It's a discrete signal. These valves, all of them, these are the binary signals to action. So we don't have a analog output to control these signals. We have the discrete signals. We have 6 discrete signals, one for compressor 1. The next one is the 75% capacity. The next is the 100% capacity valve. These are controlled by solenoids. These are the capacity valves. And the same for compressor 2 and 2 other valves to control the capacity for the next compressor. We have a priority option. Which compressor is prior? We need to consider that. If compressor 1 is prior, the condition should be we need to start compressor 1 the first. We need to start compressor 1, then the valves for 75 and 100 capacity, and next we need to start compressor 2 capacity. But when compressor 2 is prior, we need to start compressor 2, 75 here and 100 here, and then we go to compressor 1. So priority is important for changing the roles. We cannot use the conventional PID loops. We just simply create a simplified version of a PID controller. We have the set point here. Let me change set value to 10. The set value is limited to 45, and I think it cannot be less than 10. So it's between 10 and 45. If you want to have a less than 10, if you want a set value less than 10, you will encounter an alarm, and clearly you have option to change these values in area. In here, let me show you where it's possible to change this set value. Let me see, we have a chiller in CFC, we have a chiller and a void. In chiller, set point in is here, and it's limited to 10 and 45. You can manipulate these variables in order to achieve what you want, but 10 and 45 is more realistic. Cycle is considered to be 100 ms, 100 millisecond. Dead band of control is 1 degree centigrade. We just interested in half of this value. If you increase the dead band, you will have more inactive region. As an example, if your set value is 10, the inactive region will be 10.5. The 10.5 and 9.5. This region can consider to be inactive. If you want your motors, if you want to send command on the motors in a longer period, if you want to keep them safe, you can increase the pulse and increase the deadband. But when you increase the pulse and increase the deadband to protect the electrical part, the process may respond more sluggish. As an example, you can increase the pulse to 60 and deadband to 4. In this manner, the on-off commands on compressor and valves will be will be longer. You need 60 seconds to check the status and send the signal. If the whole command, the whole capacity control will be 6 states. We start from, if the priority is compressor 1, we start from here, 3 states, here, and here, 6 states. In each 60 seconds, the pulse or the period that we select here, in each 60 seconds, we create a pulse and check the status. If you want to commission this system in actual working machine, you need to increase the pulse. To protect the electrical devices. But for simulation here, we decrease the pulse to 10 seconds and deadband to 1 degree centigrade. Priority is 1. When priority is 1, let me see, when priority is false, Ka is prior. We will see what, let me see the priority signal here. Priority. If priority is 0, 1 is prior, and if it's 1, we start from the compressor number 2. We can test it. We change it to 0, and let's see what will happen. I will show you the operation of the compressor. First, let me show the operation, and then I will explain the program inside. We have set point of 10, and I should start the logic. When I start logic, you can see that the we need to reach to a lower temperature here. And first we start with compressor 1. The inlet pressure for compressor is 2. We should have the increase in pressure here, and the temperature is decreasing. Based on the set point and actual process value, we increase the capacity. The capacity is increased in each 10 seconds. We increase the capacity in each 10 seconds. We increase the capacity, so we need more pressure, more pressurized refrigerant here to decrease the temperature. You can see we need more capacity. Compressor 2 is working in 75%. Now it's in full capacity. Compressor 1 is prior, and it's also in the full capacity. So we will wait, and we should see that we should reach to the 10 degrees centigrade, and you can see that after starting, the temperature is decreasing here. The temperature is decreasing, and when we reach to the set point and the dead band, I think it should be around 9.5. The capacity will be decreased in order to maintain the temperature. These are binary signals, and we cannot use the conventional PID controllers. And as we have we have 6 actuators, we can control the whole process by these actuators. So when we reach to 10 minus half of the deadband, 9.5, the capacity will be decreased in each 10 seconds. The 10 second is the pulse or the update period for us. I will explain the program in the next section. 17, 16, when we reach to 9.5. We are in 10.35. We are getting close to the set point, and now the capacity is decreasing. The capacity is decreasing. The capacity is decreasing here. Let me check the trend. We are reaching to the set value. We reach to the set value. If you select a very tight dead band and very shorter pulse, the electrical part of the electric part of chiller will be in danger of being damaged, because they should be more active, and I will run another test for you, and in the next test I will increase the deadband and increase the time, the cycle, the pulse, the period to check and update. The period I changed to 60 seconds, and deadband I will increase the deadband. You can see that electrical parts are working to maintain the set value, and I will first I need to increase the set. I need to increase the set value to 40, and in the next test I will. You can see that when you can see that when the actual value is more than, when the set point is more than the actual value, the capacity is decreasing in each 10 seconds. The capacity is decreasing here, and the capacity is decreasing. The temperature should also increase, and that's normal. So I pause the video here. After reaching to the temperature of 40, I run the test again with new values, new pulse time and new deadband.